Hello everyone. We are back to my study tonight to examine some new scientific mysteries. This is going to take us to the far past of Earth and the evolution of life, as I tell you about the Cambrian Explosion. We will see what it is. And also to deep space and the secrets of matter and energy, when we explore what is called dark energy. This may sound a bit complicated, but don't worry. As usual, we will try to go beyond the surface and discover some relevant concepts and mechanisms, but it will all be beginner-friendly and easy to understand, even if you have no knowledge of paleontology, astronomy, or physics. Before we begin our exploration journey, please make yourself comfortable. Do not hesitate to close your eyes, and if you feel like letting go at any time during my talk, just let it happen. You can always return later and continue the story. So let the tension go in your shoulders, your arms, your legs, all the way down to the tip of your toes. For the next hour or so, we are going to discuss facts and theories about the physical universe or the evolution of life that are way bigger and significant than anything that may happen in our lives. They provide good reasons to get out of our own heads for a little while. I also invite you to check other ways of listening to my stories, if these are more convenient for you. You always have the possibility to join my Patreon page if you wish to support this channel and get more of it, with downloads, all the stories with background sounds, surveys, advanced releases, a chat for members. Patrons can also listen to the podcast version of my channel on Spotify or Apple Podcasts and other podcast apps. You get a private link to do it when you join Patreon. You can also listen to these stories on music platforms and a few apps like Aura or Slumber. There are links to these in the description box and the first comment pinned under the video. And finally, this is the time to announce my return to episodes in French after I think something like 5 years. In less than 2 weeks, I will launch a new channel and podcast, La Bibliothèque des Rêves, with French versions of the talks you listen to here, like the podcasts Lights Out Library and La Biblioteca de los Sueños that I make with Olympia, who is American but speaks flawless Spanish and edits and records again the stories with her own twist in English and Spanish. But I will also be the narrator of the French version. I'll let you know on my channel and on Patreon and Facebook when this is available. And now, let's begin our exploration journey of the night, which is going to start with a huge jump to the past of Earth. Let's examine the question raised by the Cambrian Explosion. And first, what is this? The Cambrian is a period in the geological history of Earth, a long period of more than 50 million years, that began about 540 million years ago and ended about 490 million years ago. This is way older than the time of dinosaurs and Earth would have been unrecognizable to us. There was no vegetation on the continents, nor any visible fauna on the land, and the world map had nothing to see with what it is today. Most of the continents were located in the southern hemisphere. A large landmass called Gondwana that comprised almost all of what is now Africa, South America, India, Arabia, Australia and Antarctica, concentrated about 2/3 of today's continental area on the planet, and Laurentia, a smaller continent that comprised modern North America and Greenland, lay near the equator and was separated from Gondwana by an ocean, Iapetus, that opened due to plate tectonics as the Cambrian advanced. So the Earth was very far from what it now looks like, but life had already appeared on it. Hundreds of millions of years earlier, actually. Unicellular organisms, microscopic bacteria and algae that had already slowly but surely changed the chemical composition of the atmosphere. They used the energy of light of the sun to break the carbon dioxide molecules dissolved into the Earth's oceans. And breaking these molecules generated energy. They also used carbon to build and maintain their organisms, and rejected oxygen, the subproduct of their life cycle, into the water. This had oxygenated the Earth's oceans, increased the quantity of oxygen trapped into them, to the point that after hundreds of millions of years, they had ended up saturating the oceans in oxygen. And as the seas could no longer absorb oxygen, because they were full of it, it had started to escape into the atmosphere that had been oxygenated too, preparing the Earth for the kind of land life and life forms that would appear in later periods. I'm telling you this because the Cambrian is known, first and foremost, for the multiplication of life forms in variety and size that happened during it. Before the Cambrian, life forms had been mainly unicellular. Multicellular organisms had also appeared before it, but they had remained very small and relatively rare. During the Cambrian, this changed dramatically. Species multiplied, way bigger organisms appeared. Life seemed to radiate in many different directions. This is what the Cambrian Explosion is about. An explosion of animal life. An explosion during which some basic rules of animal life seem to have been defined and are still valid. For example, the appearance of most major phyla. A phylum, in the classification of species, is a relatively high level of classification. It is below a kingdom. There are only 5 or 6 kingdoms of life, and these kingdoms include Animalia, the animals, Plantae, the plants, fungi, bacteria, protista. There are still debates about the number and exact perimeter of some of those kingdoms, but it doesn't matter here. There are very large categories of life forms. And a phylum, phyla in the plural, are the levels of classification just after that. They correspond to the body plan of life forms, what organs, how they are connected, how many limbs, and for what, that kind of things. For example, the animal kingdom, Animalia, has 31 phyla. The plant kingdom, Plantae, only 14 phyla, and the fungus kingdom has only 8. Most of these phyla, so that is to say, the big picture of how the bodies of life forms are going to function, what they will look like, so the big strokes, most of these were defined during the Cambrian. Now the term explosion or event about the radiation of life during the Cambrian can be a bit misleading, because it suggests it happened extremely fast. It was very fast on a geological scale, and compared with the evolution of life before. But in reality it was still over millions and millions of years that it took place, which means that at the scale of a human life, that would have been completely imperceptible. It is an explosion in the geological sense of the term, because geologically, 1 or 2 million years is not much on a planet that formed 4.5 billion years ago, 4,500 million years ago. The Cambrian lasted for about 50 million years, and this explosion itself is estimated to have lasted about 20 to 25 million years. But some researchers see it as even shorter, maybe 5 to 10 million years. And it would have happened at the beginning of the Cambrian, roughly 540 to 520 million years ago. So, how can we know that life exploded more than 500 million years ago? Because of the fossil record mainly, which still exists in various geological layers around the world. Layers that formed by sedimentation, the accumulation of matter that slowly settled to the bottom of oceans generally. And in these layers, fossils of animals, at least the ones that had bodies that fossilize, this is relatively common for hard-bodied animals, and less so when they only have a soft body, but not impossible. So in these layers, fossils of marine animals have been preserved for more than 500 million years. And they inform us of what life was like and looked like back then. Before this Cambrian explosion, during the previous period, which is called the Ediacaran, there was this limited number of multicellular organisms that appear to have been mostly soft-bodied, jellyfish-like creatures, thought to have been rather simple. And suddenly, in the fossil record, with the Cambrian explosion, an incredible variety of more complex life forms appears. Animals with shells, hard shells, that fossilize well, animals with skeletons, and a more intricate body structure. I told you that the major phyla appeared at the time. That includes arthropods, for example trilobites, mollusks, echinoderms, the first ancestors of starfish, and also chordates, a very important phylum, because all vertebrates, like us and so many other species, are chordates. Animals with what is called a notochord, a flexible rod, along their back, and a dorsal nerve, a spine. It is believed the very first chordates appeared before the Cambrian, but they really multiplied and grew during the Cambrian explosion. Another major aspect of the explosion is the appearance of hard parts. Animals using calcium carbonate or other materials to build bones, forming skeletons, exoskeletons or hard shells, which is also why the fossil record became so much more abundant. These body parts fossilize much better than soft tissues. And yet another salient dimension of the explosion is the appearance of what is called ecological complexity. That is to say, complex and evolving food chains with predators and prey, so the appearance of predator-prey relationships. Burrowing behaviours too, that is to say, prey developing protection strategies of all kinds. All of this with way more species than before. Hunting, hiding, competing for resources. These are all behaviors that are thought to have appeared with the Cambrian explosion. So in summary, all of this to illustrate the crucial, pivotal moment that represents the Cambrian for life on Earth. It is not the only big radiation of life. There are others identified by paleontologists. For example, during the following period, the Ordovician. And it could be argued that life has radiated and grown again multiple times at the junction of the following geological periods. They are defined by these extinctions followed by phases of recovery. But the Cambrian explosion is singular because it is the earliest, the first one identified, because it set many of the rules or of the laws that would govern life forms to our days. And its scope, its level of invention of body plans, of organs, body parts, ecological mechanisms, this remains unmatched. And this brings us to our mystery here. Why? Why, after hundreds of millions of years of very slow, almost imperceptible evolution of life, why this sudden burst? What kind of event, change of condition, or threshold effect maybe, could have triggered this? It is not that we lack explanations. There are several that I'm going to tell you about. But we don't know which one, or which ones in combination, are the main responsible for the Cambrian explosion. So let's review them. A first mechanism could be oxygen levels. I told you before that leading up to the Cambrian, oceanic and then atmospheric oxygen levels had risen significantly as a result of the colonization of oceans by organisms practicing and living of photosynthesis. This could have been important, because maybe more oxygen would have supported the energy needs of larger, more active animals with complex metabolisms. Oxygen may have been the limiting factor for the evolution to larger and more diversified organisms for a long time. And suddenly, when this limit was removed, it happened. That would be a typical threshold effect taking place in the environment. That's hypothetical. We know that oxygen levels were on the rise before and during the Cambrian. Another valuable information from geology. But we cannot affirm that this was what organisms needed to multiply and grow in size, because we don't exactly know what their behavior and metabolism were like. But that's a sensible guess. Possible factor number 2 is that it could have been due to the appearance of genetic innovations. No body plan, body functions, or development can exist without genes that carry the information needed, especially developmental genes. What is called developmental gene is any gene that plays a role in the growth, the organization, and the differentiation of cells. Our cells are not all the same. We have brain cells, liver cells, blood cells, and so on. And we need all these different cells with their respective functions and locations for our bodies to work properly. They all appear as we develop, even though initially we were all a single cell that became an embryo when it split into 2, then 4, then 8 cells, and so on. But soon enough, in the development of an embryo, the initial packet of cells starts to take a shape. It evolves towards the body shape of what the viable individual will have. And the variety of cells increases as organs and skeletons and limbs form. All this information, this program, this potential, was already enclosed in the very first cell, in DNA. Where cells will go, how they will be connected, their type. This is the organization and differentiation of cells. Over time, generation after generation, DNA can evolve, mutate, and the theory of evolution tells us that the viable and generally fittest new organisms that appear as life branches out will survive and keep evolving. But for this to happen, DNA, and especially these developmental genes, needed to become complex enough to carry this information. New genes can appear over time as a result of life forms experimenting and going through mutations. An example is Hox genes, HOX, which are the ones that determine body segmentation and patterning along a head-to-tail axis. Another example is PAX6, PAX, a gene that is crucial for the development of eyes. It is believed that these particular developmental genes appeared a bit before or during the Cambrian Explosion, meaning that with the same basic bricks of life, once they were here, it was now possible to build way more complex and bigger organisms. Here again, opening a new world of possibilities. And this could be the main factor behind the Cambrian Explosion. The liberation of a potential that these new genes unlocked. Now, however seducing this explanation may be, we don't really have proof that these genes triggered the Cambrian Explosion. We know they appeared. That's a logical guess because without them, the life forms from the fossil records could not have been possible. But we don't know with certainty if they caused or if they accompanied the explosion. Because of course, if you have way more species and life forms, you multiply the odds of seeing new genes. It could also be a combination of both. They would have triggered and also accompanied this radiation of life. Possible factor number 3, the explosion could be due to significant environmental changes. This is unlikely to be the only cause, but it could have played a role. By environmental change, what I mean is that the chemical composition of oceans could have shifted importantly due to geological activity and plate tectonics. Continents broke up during the Cambrian, and this could have created new habitats, giving new species a shot at appearing and diversifying. But it could also have changed oceanic chemistry. For example, calcium may have become more abundant in water, more available. As I told you before, one of the aspects of the Cambrian explosion is the multiplication of hard body organisms, typically using calcium carbonate as the material to make their shells or bones. And for these reasons, that could be a factor that contributed to the explosion. A fourth explanation, that may not be exactly a trigger, but an accelerator of the radiation of life, is an ecological feedback effect. What does it mean? When you move from a very simple ecological system, in which organisms are essentially single-cell creatures that live from photosynthesis or the absorption of chemicals that float in the water, to one in which predators exist, this may provoke a sudden shift, an arms race. Now that there are predators, their preys are going to be selected to evolve based on their capacity to escape or survive the existence of predators. And the predators are also going to change over time to adapt to the new preys. In other words, the mechanisms behind evolution appeared or changed with the Cambrian. And a single change, like the appearance of a predator, could have snowballed into a feedback loop that dramatically accelerated the evolution and appearance of new life forms and species. Yet another ecological change that could be considered a fifth factor is the end of an important glaciation that happened just before the Cambrian. In the hundreds of millions of years prior to the Cambrian, there were various phases during which Earth may have been partially or entirely covered in ice. A theory called snowball Earth that refers to periods when Earth may have been entirely frozen, including at the level of the equator. It is believed that one such period of snowball Earth happened around 700 million years ago, and yet again around 640 million years ago, give or take 10 million years. In these periods, temperature on Earth would have dropped to averages around minus 50 degrees Celsius, 50 degrees below the transformation of water into ice, as a result of a climatic feedback loop that could have made the temperature of the planet drop durably. And with the entire Earth taking the appearance of a snowball, all white, so in astronomical terms a high albedo effect, this white planet would have reflected solar light instead of absorbing it like before, and this would have contributed to maintain the temperature firmly in glaciation territory for several million years. There were also lesser glaciations that were not complete. They only meant that the ice caps at the poles advanced a lot. One such partial glaciation is believed to have happened around 580 million years ago and lasted about 300,000 years. Experts still debate how big it was, but the relevant element here is that after that, when the Cambrian began, these glaciation phases became less severe, and no other occurrence of snowball Earth is thought to have happened after that. Now, as you can imagine, a total glaciation of the planet is not great for life. It means oceans under the ice cap turn dark. And if organisms live from photosynthesis only, their livelihood disappears. So glaciations may have hit life severely without completely eliminating it. First, because other organisms could live without photosynthesis, like the ones that feed on chemicals at the bottom of oceans near hydrothermal vents that release hot water rich in chemicals coming from the mantle of the planet. And even with a complete glaciation, it is well possible that small lakes or ponds of water, of warmer water, survived, for example around volcanoes, and life could have found there a refuge where photosynthesis could have continued. And after the glaciation, photosynthetic organisms could have multiplied again everywhere and recolonized the oceans. In any case, the aftermath of this last glaciation, called the Gaskir's glaciation, and of the more severe ones that had preceded it, could have permitted a recovery from these harsh conditions. And this recovery might have opened up ecological niches for new life forms to exploit, unleashing a potential that had already been there for a long time, but that had been inhibited by these episodes of freezing. So the Cambrian would have been the moment when this potential was not inhibited by glaciations anymore. So, as you see, hypotheses abound, and the triggers of the Cambrian explosion may well be a combination of all or some of them, various factors that could have converged at the same time, an alignment of the stars that would have opened the door to a jump in the evolution of life. How to evaluate the contribution of each of them, this is still an open debate in the scientific community, together with other debates about the Cambrian explosion, such as how sudden it was. Some argue that the explosion looks fast, for a large part because earlier fossils did not preserve well, and that the groundwork was more in the previous period, the Ediacaran, rather than the Cambrian. Others also argue that the diversity of life forms may be a bit overstated for the same reason. The real explosion would be the explosion of the fossil record, because of these new hard-bodied creatures. But this record may give a biased vision of the actual diversity of life. To these arguments, it is possible to reply that, in any case, the sudden multiplication of hard-bodied animals that did not exist before is in itself a major evolutionary change, an explosion. or that it is also an exaggeration to say that soft-bodied animals from before the Cambrian did not fossilize at all. They did sometimes. We have fossils of them from around the world, even taking into account that they had soft bodies and only a tiny fraction of them left traces. They do not show the kind of variety of sizes or ecological roles that appeared in the Cambrian. So, as you see, this debate about a pivotal period in the evolutionary history of Earth is still open and could continue to evolve in the next few years. Our second mystery of the night is going to make us travel too. But not in time, in space, and far beyond our galaxy. Let's talk about dark energy. And first, what is dark energy? Maybe you heard already about another concept called dark matter, which is different. But quickly reviewing it will help us understand dark energy. Dark matter is a hypothesis that arose when astrophysicians observed how galaxies moved in space. You know, they tend to get away from each other in space, a consequence of the expansion of the universe. But galaxies also influence each other by their mass due to the gravitational force. An object made of matter that has a mass attracts any other object. The bigger, the more massive the object, the stronger its gravitational pull, and the closer, the stronger this force is going to be. You know that this force is what is at play in our solar system. The mass of the Sun attracts the planets and keeps them in orbit around it, and vice versa. The planets attract the Sun, but much less, because they contain way less matter. It is also at play in our galaxy, which rotates around a galactic center that contains more stars, and at the very center, a gigantic, supermassive black hole. And it works between galaxies that are the most massive clusters of matter we know of in the universe. Even if they are far apart, they interact via gravitation, and sometimes they attract each other to the point of crashing and forming a single, more massive galaxy. The hypothesis of dark matter appeared because gravitation did not seem to work correctly anymore when analyzing these interactions between galaxies. Their relative speeds, their movement, did not seem to obey to what the laws of gravitation predicted. Something was off, and it was a big difference with what theory indicated, not a small one. This observation has been made and remade to the point that little doubt remains possible. Galaxies do not behave as they should based on the laws of gravitation, which can only mean one of two things. Either the laws of gravitation do not work and they are flawed as a theory, or these galaxies somehow contain more matter, are more massive than they appear to be. Is the theory of gravitation wrong? It is impossible to be 100% sure that any scientific theory is the absolute truth, obviously. But saying that gravitation is wrong is a very bold statement. Bold because the pertinence of gravitation has been proven countless times. It predicted the presence of bodies before they could be observed, just by deducting their presence from their gravitational influence on other bodies. Its predictions about the movement of planets, the presence of invisible masses such as black holes that were revealed later. It's used to predict perfectly precisely the trajectory of comets and many other examples. All of this works every day, and it has been working for a long time. We know that there are other forces at play with matter, especially on smaller scales, like the ones that keep atoms and particles together, or the electromagnetic force. And maybe, why not, other forces remain to be discovered. But gravitation is such a solid, verified, and reliable pillar of physics that throwing it through the window is difficult, nearly impossible. But why are some galaxies not obeying it, then, if it works that well? Maybe because their real mass is not the one observed. It would include bodies or particles with a mass, but that are undetectable otherwise. They would be invisible and emit no radiation that we could identify. And this mysterious, unknown form of matter that has a mass but nothing else we manage to detect, to identify, is what is called dark matter. If it exists, we don't know exactly what it is. And primarily this concept of dark matter arose as a deduction made from the laws of gravitation. So that's for dark matter. Now, what is dark energy? In a way, it is a mystery of the same kind, because dark energy is a hypothesis too, a kind of name given to a phenomenon that remains unexplained, and needs this proposed explanation for the laws of physics as we know them to keep functioning. So what is this phenomenon that has been observed and confirmed with a good degree of certainty that needs dark energy as a proposed explanation? It is the fact that the expansion of the universe tends to accelerate instead of being constant or decelerate. What does it mean? You probably heard about this expansion of the universe, and I made an episode a couple years ago about cosmology that explained in more details the ways to picture our universe and what the leading theory about its history, the Big Bang theory, has to say. According to the Big Bang theory, the universe began in a single point, a singularity, where energy and mass would have been infinite, more than 13 billion years ago. And this single point expanded into our universe, containing all the matter and energy in existence. Since then, this expansion never stops. It continues right now. How do we know it, and why is the Big Bang considered a credible theory, a credible description of what happened? First, because it is coherent with the observed expansion of the universe. Galaxies travel in space, and faraway galaxies move away from each other. The Big Bang also explains observations made about the universe cooling down since it started to expand. Second, because as any good theory, the Big Bang theory allowed to make predictions that were later proven to be correct. Especially something called the microwave background, a major piece of evidence. The math of this is complicated, but the concept is simpler. The idea is that way back when the universe was still like a soup of very hot particles, only a few 100,000 years after its appearance, which at the scale of astronomical times was not much, still at the very beginning. So at this time, light would have been trapped by all these particles and energy condensed. Then the universe cooled down enough for atoms to form from these particles. And the light would have gotten freed, released from the constraints of this very dense matter and energy. That newly free light should have stretched out as the universe kept expanding, turning into a faint glow of microwaves, like a lasting signature of this process. This is a prediction that models of the Big Bang theory made. And later, in 1965, this ancient microwave, the cosmic microwave background, was detected by accident by a radio telescope. The two radio astronomers who discovered it won a Nobel Prize for it in the 1970s. And the Big Bang theory predicted it. There is no other possible explanation to it. And this was a huge validation for the theory, which became mainstream and very solid after that. So the expansion of the universe can be confidently considered as fact. It is observed looking at faraway galaxies. It is coherent with the story of our universe. But what is harder to explain is another observation that has also been repeatedly confirmed since the 1990s. The expansion of the universe is accelerating. Cosmic objects are driven apart at an increasingly rapid rate. And this is really strange, because as we have seen before, when I told you about dark matter, there is gravitation. Galaxies attract, they don't repulse each other. So why does the expansion of the universe not decelerate or reverse, or at least remain constant, given that gravitation, the strongest force we know of for large bodies on large scales, should tend to make it shrink? Well, we don't know. There seems to be something, a force, an energy, that more than offsets gravitation and makes the expansion of the universe accelerate. This is dark energy, an unknown thing, a hypothesis that reconciles observations and the laws of physics. Now, to understand this well, it is necessary to discard a common misconception about the Big Bang and the expansion of the universe. The name of the theory and the description of what happened suggest that the universe appeared and started to expand in a void, like an infinite void in the middle of which suddenly an explosion would have taken place. And since then, an ever-growing universe would expand. This is not what the Big Bang Theory says. The void itself, anything we can conceive, is part of the universe. It is inside it, not outside. There is no void around it. And this is hard to picture in our minds, because we are tempted to say, well, if the universe expands, then it must have an edge somewhere. And if we were on the edge of this universe, we could still go further into the void. Actually, no. But this is because a probably better way of picturing the universe is to imagine it like the surface of an inflating balloon. The universe is not the air inside the balloon. It is just, in that metaphor, the rubber surface of it. If you imagine 2 points close to each other drawn on the balloon, as the balloon grows bigger because it is being inflated, the 2 points are going to move away from each other. We could say that they move, that they travel, but it is essentially because the fabric of their universe, this balloon, is inflating, which increases the distance between them. And if we stick with this image of the balloon, you see that the universe can expand and expand without having an edge. It just becomes larger without conquering any void near its limits. It inflates instead. Of course, that's just an image. The real universe has more dimensions than that. And its fabric is not the two-dimensional rubber wall of a balloon, but space-time according to modern physics. But still, this balloon is probably a more pertinent picture of our universe than imagining galaxies traveling always further in a pre-existing void. And returning now to dark energy, this form of energy would be a kind of counterpart to gravity, an anti-gravity force, or, in other words, an element that provides a negative pressure that stretches the fabric of the universe. Typically, pressure shrinks things. This is why it is called negative pressure, because dark energy would do the opposite, stretching things. But what is the exact nature of this force? How does it work? We don't know that. That's the mystery. Another problem is the magnitude of this unexplained force or mechanism that makes the universe accelerate its expansion. In order to reconcile the dark energy hypothesis with observations of the acceleration of the universe's expansion, dark energy would have to account for, to represent more than 2/3 of the whole universe, of its entire quantity of energy and matter. Why mix energy and matter? Because another big leap forward of 20th century physics and the theory of relativity is the understanding that energy and matter are not that different. They are also two states of the same thing. Matter is potential energy and vice versa. They can be interchangeable. And even though it may be another thing that we have a hard time picturing, we have tangible proof of it. For example, in particle accelerators, high-energy physics, it has been confirmed, observed, that energy can be converted into new particles with a mass, or in nuclear reactions, like the fusion reactions that happen in the sun. when the fusion of hydrogen atom nuclei takes place and a lot of energy is liberated under the form of heat, light, kinetic energy, a small amount of mass disappears, it is lost. The new atom has slightly less mass than the previous two. Actually, the equivalence between mass and energy is what the famous equation of relativity, E is equal to mc squared, reflects. E is energy and m is mass in that equation. C squared is a constant, so there is an equivalence between the quantity of energy and the quantity of matter, the mass. Finally, another illustration that mass and energy are like two sides of the same coin is the fact that both exert the same influence on space-time. They can curve it the same way. This is one of the highlights of the theory of general relativity, and this also shows the equivalence between matter and energy. So I'm telling you this just to explain why, when looking at what the universe is made of, the natural answer, matter, the universe is made of matter, is something that modern physicists would nuance. It is not wrong, but matter and energy are not two distinct quantities independent from one another. And it makes sense to say that the universe is made of a certain quantity of matter and energy, or to speak of its energy content. And this is why I told you that dark energy would be a big deal, because based on its effect on the expansion of the universe, it would have to account for around 70% of the energy content of the universe. 68% precisely. Add to this dark matter, that would account for about 27%, and we come to the apparently absurd conclusion that 95% of the universe is dark matter and dark energy. That is to say, things that physics cannot describe or define precisely, two hypotheses. That's probably the most uncomfortable thing in modern physics. This conclusion that appeared in the last 50 years, that around 95% of the universe would be made of something unknown. But again, dark matter and dark energy are first and foremost hypotheses, created to reconcile observation with the laws of gravitation and other theories. This being said, there are candidates or possible explanations to the question of knowing what dark energy actually is. First, it could be an unknown force, like gravitation, that remains to be discovered or understood. After all, gravitation was discovered long ago, well before other forces, like the ones that structure atoms. The electromagnetic force, or the force that binds particles in atom nuclei. It is possible that another fundamental force of physics, a fifth one, because we know four of them, gravitation, electromagnetism, and the strong and weak forces that are at play at the scale of atoms and particles. These forces are called fundamental because they described the known physical interactions in the universe. But maybe this accelerating expansion of the universe, or the lack of coherence between the apparent mass of galaxies and their gravitational pull, so the mysteries of dark energy and dark matter are just aspects of one or several other fundamental interactions that we do not grasp yet. And we would have come up with this dark energy hypothesis out of ignorance of another force that maybe one day will be understood. Another conceptual explanation about the nature of dark energy could be a kind of energy of the vacuum in space. There would be particles popping in and out of existence in empty space for reasons that are unknown. But that could explain the presence of this energy, which in this case would be real, not another name for a force. It is just that we wouldn't have been able yet to capture, to observe these particles. This is purely hypothetical, of course, and so are other high-concept explanations. Another one, for example, would be the existence of fields of hypothetical particles called tachyons. Tachyons may or may not exist. They were never seen, but they were proposed in the 1960s by physicists working on the theory of relativity. Tachyons would have what is called an imaginary mass, not a positive or zero mass, but imaginary, which is a purely mathematical concept. And this imaginary mass would free them from the laws of relativity that say that the speed of light cannot be surpassed. Tachyons would travel faster than the speed of light, meaning also that they would travel backwards in time. Don't worry if that sounds impossible to understand. It is very conceptual and hard to picture. But the point is that if tachyons were really a thing, dark energy could be a manifestation of their existence. As you see at this point, the only honest answer to the question of what is dark energy is that we don't know. But looking for it, questioning existing models and theories, is the beauty of scientific research, and it is thanks to this that maybe, in the future, another leap forward in the understanding of our universe and possible practical applications will materialize. We have reached the end of our story for tonight. You may now let go and fall asleep, or pick another story from my library if you don't feel sleepy yet. I'll be back soon with another one. And in the meantime, sleep well. Sweet dreams. Au revoir.